Hello everybody and welcome to my video on the normal distribution. I have to admit that I think that this is probably the most important distribution that we will be working with. We will see that later on the normal distribution will have a huge part of our inferential statistics that is coming up. So this is our first introduction to what is called a continuous distribution. And later on in our course, we will be introduced to another continuous distribution called the student's t-distribution. And there are other distributions that follow a continuous distribution or as a continuous random variable. That is the beta distribution, the exponential distribution, the gamma distribution, and the Weibull distribution. And these all come up and they have their place. We probably won't see them, but for those of you that want to grow up and become an actuarian, you probably will see these quite a bit. All right. We are also going to answer that big proverbial question that all students ask when they take a calculus course, and that was, when am I ever going to use this? And the big question was finding the area underneath a continuous curve and the x-axis. So if you've taken a calculus course, your answer to that question is coming up. All right, so as always with this video, there will not be any technology introduced. I have technology tutorials that are available for you using the various technologies that are available for the course. So if you're a Pearson product and you're using StatCrunch, I've got those. And if we're going to be using the handheld computational device such as the TI calculator or an app that's on your iPhone or Android device, we'll have a separate one for that as well. So all right, so first I'd like to take a look at the formula for the normal distribution curve. This thing is 1 over the square root 2 pi sigma squared e raised to the negative x minus mu quantity squared divided by 2 sigma squared. And the parameters for the model are mu and sigma. X is the value of the random variable. So one of the things we would like to investigate here in just a moment is what effect does the mean and the standard deviation, mu and sigma, have on this curve. All right, but first let's just take a look at the normal probability density curve. So as we can see here, this function, this graph, is a bell-shaped graph, and it happens to be centered right here at the value of x equals 0. So this is a specific normal distribution called the standard normal, where both the mean and the standard deviation are 0 and 1 respectively. We can see that the curve goes out to infinity indefinitely, both to the left and to the right, and that the curve is asymptotic towards the x-axis, meaning that the curve, the graph, will never touch or cross the x-axis in both the negative direction and the positive direction. The distribution is centered or symmetric, a mirrored image about the center or the mean, okay? And notice that at the top of the hump, based upon our discussion of graphs, that the mean and the median for this curve are the same. And that shaded region underneath the curve, that shaded region is called the area under the curve, or between the x-axis and the curve. That area in there has to be 1. So for those of you that had the calculus course, you would integrate from negative infinity to positive infinity. Remember, that is areas. So that total area, since this is a probability density function, has to be 1. And let's see. So areas underneath the curve, we'll see some here in a few minutes, some special types of areas under the curve will represent probability. So now we are ready to take a look to see what happens when we have different values for the mean and the standard deviation of that density function. All right, so now we'd like to take a look at how the parameters mu and sigma have on our normal density curve. So as you can take a look here, I have some curves, a blue curve, a red curve, and a green curve. And we would like to notice that for the blue curve, the mean is -4. For the red curve, the mean is 0. And for the green curve, the mean is 3. And notice that each one of these bell-shaped distribution curves are centered at the means. So the mean is also referred to as a measure of centrality or a centrality parameter. As we take a look going from right to left, in this case, at the standard deviations, for the green curve we have 0.75, for the red curve we have 1, and for the blue curve we have 3. So as the standard deviation increases, we can see that the spread of these curves also increase. So the standard deviation sigma is also known and referred to as a shape parameter. So the smaller the standard deviation, as we learned earlier, the smaller the spread, the more clustered that area under the normal curve should be about its mean. And as you can see, moving from left to right, as sigma gets bigger, the curve gets wider, and all of these curves still have to maintain an area underneath it of 1. So notice that the blue curve is short and wide, and the green curve is tall and narrow. So the mean is a centrality or a measure of center, and the standard deviation is a shape parameter. So the bigger the standard deviation, the wider the curve should be. All right, so to bring out this idea of probabilities regarding the normal distribution, we need to take a look at areas underneath the curve. So the normal distribution, or the normal probability density function, is a continuous random variable. So that means that we have to have an interval to compute probabilities. All right, so one of the things that we can have is what is called a left-tailed area. So as you can see in this picture that I have, you can see that the area to the left underneath this density function is shaded to the left. So that this would be computing a left-tailed area. Whereas we have on the opposite side the right-tailed area. So we can compute the area that the random variable is whatever value that is all the way out to infinity. And that's very important that you need to realize infinity is where both that left-tailed area and that right-tailed area head out to. And then finally, we have our last curve where we have that this region is shaded between a lower bound and an upper bound. So in the tutorial videos that I have with the technologies, we will actually talk about computing. How do we compute these areas? And these areas then will translate into probabilities. All right, so this completes my video on the normal distribution, and I hope you found that introducing these properties, the things about the normal distribution, the shape, the spread, and finding areas underneath these curves. So please take some time and go watch how to use technology. And notice that I've been pushing technology just due to the fact that probably in your reading, the authors will talk about using tables, these standard normal tables. We can kind of bypass that. That's kind of 1750s math. And since we live here in 2021, we technically really don't need to have the standard normal distribution tables to compute probabilities, but I'm not going to sell them short because in the next half, going backwards, that is, given an upper-tailed, given a lower-tailed, or given a middle area, we do want to go back and find z-scores and then transform those z-scores back to x values if we have those. But the z-scores, that concept, is going to play an important role when we get to confidence intervals and hypothesis testing. So as always, I will see you in the classroom. Hasta la vista, babies.